I hope you're doing well. Today we're going to talk a little bit more in depth about buffers, so let's go ahead and get started. Okay, take a minute to answer this question on your problem sheet, and then we'll go over it. Awesome, so we're trying to see whether each of these four solutions would result in a buffer. So with solution A, we've got some HF and a similar, not exactly equal, but pretty similar amount of NaF. Right? In that case, we have a weak acid that's HF, and we have its conjugate base, F minus. So yes, that's going to work as a buffer. Solution B, we've got HF and HCl. Those are two acids. They will not work together as a buffer because there is no way to compensate if we add more acid. These are both acids. They can't react with acid. So that's not a buffer. Solution C, we've got some weak acid and then a strong base, and we've got equal amounts of both. So in fact, with solution C, these are just going to react together. That will happen with solution D as well. Solution C and D, we both have HF and NaOH. So in both cases, you're going to actually have this reaction. But in the case of solution D, we actually are going to end up with a buffer, which is a little bit counterintuitive because we're given a weak acid and a strong base, and if you remember from last time, the definition of a buffer is you have to have a weak acid and a weak base and its conjugate base. So we need to look a little bit more closely at what's going on with answer choice D. In both C and D, this reaction is going to happen, right? HF and NaOH are going to react to make water and NaF. In reaction C, we've got the same amount of HF and NaOH, so all of it's going to react to make water and NaF. So in the case of answer choice C, it's basically the same as saying, okay, we've got a solution with a bunch of water and, NaF, right? And that's it. So that's not a buffer because we just have the conjugate base, but we don't have any of the weak acid left over. It's all reacted. However, if we look at answer choice D, we've got half as much sodium hydroxide as we do HF. So what's going to happen is this reaction is going to happen, but sodium hydroxide is going to be limiting. And so we're going to end up reacting half of the HF to make NaF, but the other half of the HF is in excess, and so it's going to be left over. And so what's going to happen is we're going to end up with a solution that has roughly equal amounts of HF and NaF floating around. And so we've got our weak acid and its conjugate base, so this is a buffer. So you want to be careful when you're looking at solutions and trying to decide if they're a buffer or not. That can get a little tricky, right? A solution like D, if you just look at the formulas, it doesn't look like a buffer because we have a weak acid but a strong base. But if you actually look at the volumes and you think about the chemical reaction that's going on, we're going to end up with roughly equal amounts of HF and NaF. So this actually is a buffer. So you got to think a little bit closely. All right, we're going to watch a quick video of a pretty neat demo. So what we saw in that video was solutions that changed color based on the pH, right? So originally they poured a whole bunch of base into all of those solutions. We saw those beautiful colors. And then when they dumped them into a strong acid, they turned clear. Right? So that was an example of a whole bunch of different indicators. An indicator is just a substance that changes color based on pH. And we've talked about these a little bit in the past. Later on today, we're actually going to talk about how indicators actually work and what's going on with them. But first, there's a couple of big ideas about buffers that I want to talk about. Take a minute to pause the video and answer these two practice problems. We're going to go over them in a second, and then we're going to talk about the implications. Okay, so let's go ahead and solve this. We can solve this the long way using an ICE table, but we can also solve it a lot more quickly using the Henderson-Hasselbalch equation, the buffer equation that we talked about yesterday. So here's the Henderson-Hasselbalch equation, right? pH is going to equal pKa plus log times the concentration of base over concentration of acid. We can go ahead and plug in the numbers we have in this problem, right? So we've got negative log of our Ka value, right? pKa is negative log, plus log, and here's the concentration of the base, the Cn minus, divided by the concentration of the acid. Well, the base and the acid have the same concentration. So we're really taking the log of 1, because the ratio is 1. Okay, so that means we're looking for 10 to what power is 1, right? Well, that's 0. 10 to the 0th power is 1. So this whole term in our equation is really just 0. And so we end up with a pH just equaling the pKa, which in this case is 9.3. Now if we look at the next part, we've got 0.5 molar HCN and 0.5 molar NaCN. When we use the Henderson-Hasselbalch equation, right, pH is still going to equal pKa, that's the same, plus log. Now we're going to have 0.5 over 0.5. So we have more concentrated acid and also more concentrated base. But the ratio is still the same. We had a 1-to-1 ratio, and now we still have a 1-to-1 ratio. And so we're still going to have the same term in our equation. Right? The actual values of the base and the acid don't matter. It's the ratio that matters. And since we still have the same ratio, we're going to get the same pH value of 9.3. So it turns out that the actual concentrations of the acid and the base don't matter in determining the pH, right? It's the ratio of acid to base, or the ratio of base to acid, that determines the pH. Okay, so does the concentration of the acid and the base matter at all? Right. It turns out it does. So take a minute and think about, can you think about any reason that the concentration would matter, right? Which of these solutions would be a better buffer and why? Cool. We're getting at the idea of something called buffer capacity. Buffer capacity is the amount of acid or base that a buffer can neutralize without significantly changing its pH. In other words, without stopping behaving like a buffer. The larger the concentrations of acid or base, the greater the buffer capacity. Right? So in these two situations, we have the exact same pH, but this solution that has larger concentrations has a larger buffer capacity. This solution is going to be able to handle me dumping in a larger quantity of acid and a larger quantity of base, because I just have more acid and base floating around in my solution. Right? In this solution, if I were to add another 500 milliliters of, let's say, 0.02 base, 0.02 molar base, right, there's not enough acid to react with it. And so the acid would all get used up, and then the buffer would stop behaving like a buffer, and it would start just behaving like a normal solution that I'm adding base to. In this situation, because I have larger amounts of acid and base, just stoichiometrically, this buffer can handle larger amounts of strong acid and strong base being added to it. So the larger the concentrations, the greater your buffer capacity, the greater the amount of acid or base that you'll be able to add without noticeably changing the pH. We can also explain that based on the Henderson-Hasselbalch equation, right? So the going to equal pKa, which is constant, plus log times the concentration of base over concentration of acid. The larger your starting concentrations of acid or base, the more that this ratio is going to stay roughly constant, right? So if I'm starting with a molarity of 1 molar acid and 1 molar base, and I add a small amount of strong acid, those concentrations won't change very much, and so this ratio will stay roughly the same, and the pH will stay roughly the same. But if I started out with a concentration of 0.01 molar acid or base, then when I drop in a little bit of strong acid, that ratio is going to change more dramatically. The ratio is going to basically change by a larger percent, and so the pH will also change by a larger number. Cool. Another thing that I wanted to talk about when it comes to buffers is their pH range. So the pH range is the range of pH values over which a buffer essentially works, or works effectively. A buffer can't work as a buffer at any possible pH. Instead, we can use the Henderson-Hasselbalch equation to explain what's going on. In order for the buffer to function, you need to have pretty big concentrations of base and acid. So generally, you're going to need them to be roughly equal. They definitely don't have to be exactly equal, but they should be on the same order of magnitude. Right? If the concentration of base is 1 molar and the concentration of acid is 0.1 molar, yeah, that's probably fine. But if the concentration of base is 1 molar and the concentration of acid is 1 times 10 to the negative 7 molar, right, your buffer's not going to function properly. Right? There's not enough acid in the solution to react properly if you add strong base. So what you need in order for a buffer to work properly is for the concentrations of acid and base to be roughly equal, differing essentially by no more than a factor of 10. Well, if they're exactly equal, right, then we have log of 1, and so this term disappears, and so the pKa is equal to the pH. That's the value, that's the pH where your buffer is going to work the best. Okay. And this ratio can basically differ usually by a factor of 10, which then, since we're in a log scale, essentially means that pH can differ by about 1. Right? So if you're dealing with a weak acid that has a pKa of 10 to the negative 4, that has a Ka of 10 to the negative 4, the pKa would be 4, right? That means that that buffer would function decently over a pH range of 3 to 5, but any other pHs, and it's not going to work. So it's always best to choose an acid with a pKa that's close to the pH that you want. So far, we've been using the Henderson-Hasselbalch equation to think about what concentrations are going to get us the pH that we want. But we can also use it to think about, okay, based on the pH, what's going to be the ratio of concentrations, right? And so we can essentially use the Henderson-Hasselbalch equation to evaluate the protonation state, whether our anion is protonated or not, right? So when we say something's protonated, we mean it has H+. So for example, HF would be a protonated molecule, right? When something's deprotonated, it's lost H+. So for example, F-. Right. So when we're talking about something being protonated, we're really talking about essentially the weak acid. When we're talking about something being deprotonated, we're talking about its conjugate base. If we look at the Henderson-Hasselbalch equation, we can actually use the Henderson-Hasselbalch equation to find the ratio of base to acid. Right. So log of concentration of base over concentration of acid equals pH minus pKa. If the pH and the pKa are equal to each other, right, then we have 0 equals log base over acid, so take 10 to the power of both sides, and we get 1, right, so we get a ratio of 1 to 1. Right, so if the pKa equals the pH, then the concentration of the base will equal the concentration of the acid. Okay, so my question to you all is, if the pH is larger than the pKa, what's the predominant protonation state, right, protonated or deprotonated? And if the pH is smaller than the pKa, what's the predominant protonation state? Take a minute and think about that. Okay, so if the pH is larger than the pKa, that means that this is going to be a positive number. So when we take 10 to the power of a positive number, we're going to end up with a ratio that's larger than 1. And so we're going to have more of the base than we are of the acid. So if we have a high pH, we're going to have more base than acid. If the pH is less than the pKa, this whole side is going to be a negative number. So we're going to have 10 to the power of a negative number. If we have 10 to a negative power, that's going to give us a number that's less than 1. So that means that we're going to have a larger concentration of acid than we will of base. And so this kind of makes sense, actually, right? Essentially what this is telling us is that the pKa is the sort of like sensitivity tipping point for any particular weak acid, right? And if the pH is lower than that, we're kind of more acidic than the acid can handle, and so predominantly the acid will end up being protonated. If our pH is above that, we're like more basic than the acid can kind of handle, and so the acid is going to mostly end up being deprotonated in its conjugate base state. And so now we can use that to kind of explain what's going on with indicators. It turns out that every indicator is actually just a weak acid that has a conjugate base and a weak acid that are different colors. And so an indicator is just a molecule that has like 2 different colors based on whether it's protonated or deprotonated. And each indicator changes color when the pKa equals the pH, right? At a pH that's below the pKa, it's going to be one color. At a pH above the pKa, it's going to be a different color. So for example, methyl orange changes around a pH of 4. If your pH is less than 4, it's going to turn red. If your pH is more than 4, it's going to turn yellow. So the acid state, the protonated state of methyl orange must be red, and the deprotonated state, the conjugate base of methyl orange, must be yellow. Cool. Okay, so let's look more specifically at bromcrystal green. Bromcrystal green has 2 forms, and I actually put in the Lewis-Dot structures for both of these, right? So here's the acid version, right, which is yellow. The acid version of bromcrystal green can lose this proton, and so this oxygen can become negatively charged, and if that happens, then there'll be a resonance structure where these 2 oxygens are actually sharing the negative charge. And this compound is blue. So I want to know at which pH will bromcrystal green transition, and what color will it be in a neutral solution? Okay, so it's going to transition when the pKa equals the pH, right? So that's at a pH of 4.8, right? That's just taking the negative log of the Ka value, right? Based on the Henderson-Hasselbalch equation, when the pH equals the pKa, the concentration of the base equals the concentration of the acid. So when the pH equals the pKa, the concentration of this blue chemical is going to equal the concentration of the yellow chemical, and we're going to end up with a solution that looks green, right? At a pH below that, we're going to have a higher and higher ratio of yellow to blue, and so as we get lower and lower pH, we're going to get a yellower and yellower green until it just looks completely yellow. At a pH that's higher than that, we're going to have a higher ratio of blue to yellow, and so the color is going to look bluer and bluer and bluer until eventually it just looks blue. Cool. And then if we want to know at what color it is in a neutral solution, okay, so that means a pH of 7. Well, pH of 7 is above the transition point. And so if we have a pH that's higher than the pKa, then the compound is going to be predominantly in its base state and its deprotonated state. So for bromcrystal green, that's blue. So we're going to have a blue solution. Cool. Take a minute to answer the next few practice problems on your sheets. All right, so we're looking at a solution that's going to be buffered at a pH of 4.3, right? We need to buffer it exactly at that pH, and we have the choice of all of these acids. And we want to know which one's going to work best, and we want to know the ratio that we're going to need for each of them. So cool. If we want to know the ratio for each, we can use the Henderson-Hasselbalch equation. Right? I'll just show this out for A, and the calculation for B, C, and D is similar. We know that we want a pH of 4.3. We can do the pKa. So we've got the pH minus the pKa. For the case of chloroacetic acid, when you take the negative log of this number, you get 2.87. So we've got 4.3 minus 2.87. That equals log of the concentration of base over acid. So to reverse the log, we take 10 to the power of both sides. So 10 to this difference, which is 1.43, equals the ratio of base to acid. So we've got a ratio of base to acid of 26.9. That's not very good. This is not a very good buffer if we want a pH of 4.3. This buffer works better around a pH of 3. We're a little far from that pH, right? And so we're ending up having to have a pretty extreme ratio of base to acid, which is not going to work very well. Essentially, we're going to have a lot of base and not very much acid. And so this buffer will work like pretty great if we add some strong acid, like the base will neutralize the strong acid. But if we add a bunch of strong base, like there's not going to be very much acid in the solution to deal with the strong base. And so this is not going to work very well at this pH. Cool, you can do a similar calculation for the other three. And here are the ratios you get, right? So 26.9, 0.269, 1.27, 0.000698. And what we want is we want a ratio that's close to 1, right? And so we get that with benzoic acid. That's the closest to 1. Benzoic acid is going to work great at a pH of 4.3. Awesome. If we look at question 2, which is a different number on your problem sheet, which of these solutions has the greatest buffering capacity? We're looking for big concentrations, right? The bigger the concentrations, the better our buffer is going to be at being able to deal with adding large amounts of acid and base. So that's going to be answer choice B, right? That has the largest concentrations. Answer choice C has concentrations that are exactly equal. So like maybe some folks might have picked that. But it turns out like it doesn't matter. The concentrations don't have to be exactly equal. What matters is that they're roughly equal, right? And different by no more than a factor of about 10, and that they're large, right? We want for the greatest buffering capacity, we just want the largest concentrations. Cool. Go ahead and calculate the concentration of H plus in a buffered solution containing 0.1 molar HF and 0.3 molar NaF. We can do that, again, using the Henderson-Hasselbalch equation. pH equals pKa plus log concentration of base over concentration of acid. We can go ahead and plug in the Ka value, the concentration of the base, or the base is F minus, that's 0.3, and the concentration of the acid, which is 0.1. And then when we do out this calculation, we should get a pH of 3.62. And then let's quickly take a look at that last problem. All right, let's take a look at this last question. So we have two different amino acids, right? Amino acids are the building blocks that make up proteins. And the amino acids have different pKa's, which are given. And we want to know the predominant state of each one, whether it's going to be protonated or deprotonated at these different pHs. This is really 4 questions, right? At a pH of 7, right, if we look at a pH of 7, that's less than cystene's pKa, but it's higher than the pKa of glutamic acid. And so cysteine, if we're at a pH that's lower than its pKa, then essentially the solution is like more acidic than cysteine can handle. And so cysteine is going to be protonated. It will have gained hydrogens off of that solution that's like too acidic for it. Glutamic acid, we're above the pKa of glutamic acid. So we've got a solution that's essentially like too basic for glutamic acid. And so the base is going to be like pulling off hydrogens. And so glutamic acid is going to be deprotonated. So at a pH of 7, this is going to be protonated. This is going to be deprotonated. Right? At a pH of 3, we're now below the pH of both of these. So we've got a solution that's more acidic than either of these. And so cysteine and glutamic acid would both be protonated at that pH. Awesome. Let's take a look at that last FRQ problem. Answered on your own. We're going to go over it. I'm going to do it on paper because I don't want to do it in PowerPoint.
All right, let's take a look at this FRQ. For 1AI, it's asking us which of the two acids is stronger, HOCl or HOBr. We can see from the Ka table that HOCl has a larger Ka value, and so that's going to be a stronger acid, right? Remember that Ka is essentially measuring how acidic an acid is. So a larger Ka value means it's more likely to dissociate and it's more acidic. So HOCl is our stronger acid. For 2, we're asked to draw a Lewis dot diagram for that acid. It's worth remembering that hydrogen makes 1 bond. Oxygen typically makes 2 bonds because it starts with 6 valence electrons. Chlorine typically makes 1 bond. And so the basic structure of the molecule is going to be like this with oxygen in the middle. And then oxygen starts with 6 lone pairs. It puts 2 into these bonds, and it has 4 more. Chlorine starts with 7, it puts 1 into the bond, and has 6 left over. And just to check, right, we can check that we're following the octet rule. For hydrogen, it's really the duet rule, right? Hydrogen has 2 electrons, oxygen has 2, 4, 6, 8, chlorine has 2, 4, 6, 8. So this molecule has both the correct number of electrons and it follows the octet rule. Good. In number 3, we're meant to predict whether HOI is a stronger or a weaker acid than HOCl. We already see that HOCl is stronger than HOBr, so if we just follow the trend down that group of the periodic table, that suggests that HOI will be weaker. We can come up, of course, with a better explanation for that. HOI is going to be a weaker acid because iodine is less electronegative than chlorine, which means it's pulling less strongly on the electrons. In this molecule, chlorine pulls very strongly on the electrons from oxygen, and so oxygen pulls very strongly on the electrons in this oxygen-hydrogen bond, which makes this bond weaker and makes it easier for the hydrogen to basically pop off. Right? Since iodine is less electronegative than chlorine, it pulls less strongly on the electrons. Pulls less strongly on the electrons it shares with oxygen, so oxygen pulls less strongly on the electrons it shares with hydrogen. So the HO bond is stronger. So looking at the answer key for the College Board, right, in order to get full points on this question, you have to both identify that iodine is less electronegative than chlorine, and that because it's less electronegative, this bond is stronger in HOI or weaker in HOCl. Cool. For part B, we're meant to write the reaction that occurs between HOCl and water. Right, that's an acid reaction. Right, HOCl is an acid, so when it reacts with water, it's going to lose a hydrogen. Right, and so we're going to form OCl minus and hydronium, just like every acid reaction. Good. For part C, we are asked to write the equilibrium constant equation, the equilibrium constant for the equation that's given to us. Right, the equilibrium constant would be the product of the products. So that's concentration HOCl times concentration OH minus divided by the reactants, which would be OCl minus, and then water does not count because it's a liquid, and liquids don't impact equilibrium constants. So that was CI. Now for CII, we're supposed to calculate this value. Right. This equilibrium constant, if you look at the reaction that this is the equilibrium constant for, it's the reaction where OCl is acting as a base. So this is actually also the Kb value for OCl minus. Right. This is the Kb value for OCl minus. OCl minus is the conjugate base of HOCl. And so we can actually get this Kb value by doing Kw divided by the Ka value of the conjugate acid. This is given to us in the problem, right? Kw we know is 10 to the negative 14. We divide that by the Ka value that's given to us in the problem, 2.9 times 10 to the negative 8, in order to get the Kb value, which I believe is 3.4 times 10 to the negative 7. Good. And then for part 3, now they want us to calculate the concentration of OH minus in a 1.2 molar NaOCl solution. So we can solve this using a standard equilibrium, right? We can use an ice table. I'm going to write in the relevant substances, right? The water doesn't matter because its concentration is irrelevant since it's a liquid. And I'm going to make an ice table. They tell us in the problem we're starting out with 1.2 molar NaOCl. So this is starting out with the concentration of 1.2 molar. You're starting out at 0. As the reaction happens, this is going to react with water to make both of these. So this is going to go down by some number, and both of these will go up by the same number since they're all in a 1-to-1 ratio. Cool, so at equilibrium, this is going to be 1.2 minus x, x, and x. And if we look at our equilibrium constant, right, it's a very small number. And so these x's are going to be really, really small. And so this 1.2 minus x is really going to be pretty much just 1.2. Now we need to solve for x. So our KEQ value would equal concentration of this times concentration of this. So that's x times x, so x squared, divided by this concentration, 1.2. And we solved for this in the previous part. So this equals 3.4 times 10 to the negative 7. So x is going to equal, we would have to do 3.4 times 10 to the negative 7, multiply that times 1.2, and then take the square root of it in order to reverse this x squared. If you plug that into a calculator, you should get 6.4 times 10 to the negative 4 molar. Cool. Okay, so that's it for part C. Moving on, in part D, they're now giving us a buffer solution. They tell us that the pH is determined to be 6.48, and in DI, they're just asking us for the concentration of hydronium. So that's actually really easy, right? We know that this equals negative log times the concentration of H3O plus or H plus, right? So we just need to reverse this. So it would just be 10 to the negative 6.48 would equal the concentration of H3O plus. So that's going to get you 3.3 times 10 to the negative 7 molar. And then lastly, DII, we're trying to figure out whether HOCl or OCl minus is going to be present at a larger concentration. So we can use the Henderson-Hasselbalch equation. That's not the only way to solve it, but it's a nice way to solve it. Right, so pH equals pKa plus log concentration of base over concentration acid. In this case, the pH is 6.48. The pKa would be negative log times that Ka value from back when we that's given in the original problem. Right, so the negative log of that is 7.53, and that's plus log of base over acid. So 6.48 minus 7.53 gets you negative 1.06. That equals log base over acid, right? So to reverse the log, we would take 10 to the negative 1.06, which is definitely less than 1. It is 0.0876. And that's equal to the ratio of base over acid. I'm running out of room on this page, right? That equals the ratio of base over acid. So that tells us that we have a lot more acid than we do base, right? So we've definitely got, I'm just going to write this over here, more acid, and then the acid, of course, is HOCl. So we have more HOCl than we do OCl minus. We can actually even see that without doing out this full calculation, although the problem asks us to do the full calculation. But we can see that without doing this full calculation just by comparing the pH and the pKa value. But our pH is lower than our pKa value. Anytime your pH is lower than the pKa value, you've got a solution that's basically more acidic than your weak acid can handle. It's more acidic than the equilibrium breaking point for your weak acid, and so the weak acid is going to be primarily in its protonated state. But as long as the pH is lower than the pKa, you're going to end up with more acid than base.
All right, folks, I hope you have a great weekend. Don't forget to vote in the SO election, and I will see you all next time.